So this is just kind of a summary of the first section in chapter 28, and also kind of a brief intro to the idea, because this section is a little different than some of the other topics we've done, because it's essentially impossible to experimentally do any of this with the equipment we have. So it's a lot more discussion of concepts and math than it is sort of experimental validity. So the first topic in chapter 28 that sort of brings us into this idea of quantum physics is about X-ray diffraction. And the important thing in this is the key, right? It's diffraction. This follows up with what we just finished last term with, right? The only reason that this is in this topic is as you'll see, it kind of applies to situations that sort of fit the realm of quantum physics, but we're really not doing anything different. We're still talking about diffraction, but now it's not diffraction of visible light, it's diffraction of X-rays. But X-rays are still just electromagnetic waves, so they're going to obey basically the same rules. So before we get into that, though, this section also has a little bit more of a historical background. Again, because some of the stuff that we're going to talk about is so strange that sort of understanding the context of how it was discovered helps you, at least it helped me anyway, believe that it's true. Because again, we can't really test a whole lot of this. So the first thing, right? We're moving into a new part of physics, sort of out of the realm of classical physics. All the stuff we've talked about was really known and completely understood prior to about 1900, 1895, that sort of range. And in fact, classical physics, Newtonian mechanics, that's AP Physics 1 stuff, and then most of the other things, thermodynamics, optics, electromagnetism, all that. All of that was so well understood that there's actually a very famous quote. I forget which physicist it was told to, but a very famous quote said by some physicist to his graduate student about like 1890. It said, "No, don't go into physics. We know everything now. There's nothing new to discover. You won't do anything new." Because classical physics was just very well understood. But right around 1900, a lot of sort of experiments started to turn up odd results. That didn't work in that realm of classical physics and forced the reinvention of physics into what we can now call modern physics, which is really quantum mechanics and relativity. So the first one of these that we're going to talk about is this understanding of what X-rays are. X-rays are named just because they're some ray that was not known, X for unknown, right? We've already kind of seen some of this, right? This is a circuitry sort of question, right? High voltages to make electrons travel very, very, very quickly, right? That's an energy conservation concept. And it turns out that when electrons travel at very, very high speeds, they radiate light a bit differently, right? I think I've shown a video of electrons traveling with kind of a green glow, right? That's when they radiate visible light. If you make them go faster, they radiate different light. And it turns out that you can't see it, right? But it does things, right? It does what's described right here. Coincidentally, this guy happened to have some photography film near his experiment, and it was exposed even though never being actually like exposed to visible light. And so he did some more testing and concluded that whatever it was something coming from this high voltage vacuum tube thing. And these X-rays behave differently. They passed through some solid materials. He continued his experiments and found that they didn't pass through everything. But this is kind of the setup of what would make X-rays. And this is still more or less what's done. Right? You have a battery, a very, very big potential difference. And you have a vacuum tube, right? So the electrons don't hit anything else and slow down. And so the electrons travel across this gap. And as they do so, they radiate some of their energy, in this case in the form of X-rays. And then they just keep looping around and around and around. So it just goes forever as long as you have a battery source that's providing sufficient power. Okay? So he did some more experiments, and he found that like these X-rays don't pass through everything, right? They pass through sort of low atomic number things, organic material specifically, right? Carbon is a low atomic number, but a lot of metals and things like that have high atomic numbers still stop them. And so you can use these X-rays to right, medically see what your bones look like, even though you have skin in the way. Right, so a very practical discovery, as some of you who have broken bones may know. At the same time, right, they tried to figure out what these X-rays were. Experiments could be done to sort of determine that these had to behave like electromagnetic waves, the speed they traveled at, the properties they had, things like that. The fact they were emitted by electrons sort of suggested that they were similar to visible light, but not the exact same. So they were able to conclude they were electromagnetic waves. And people were actually also studying sort of these atomic level properties. And it's actually very interesting to know that really prior to about 1900, there wasn't actually 100% proof that atoms existed. Even though chemists had been working with the assumption that these things, atoms, behaved in a certain way for over 100 years, there wasn't sort of an experimental proof of that, in the sense that you could like take a picture of an atom or figure out the size of an atom or anything like that. But there had ideas sort of based on the experimental results. And so X-rays were sort of being understood at the same time sort of details what the atom were being understood. And so one of the proposals, right, is this, right, that solids are atoms arranged in a nice regular pattern, and the atoms are very small, right, 1/10 of a nanometer, 10 to the negative 10th meters. And so someone put these two facts together, and from that concluded that experimentally something should happen, which is X-rays that pass between the space of atoms should work exactly the same way as visible light going through a diffraction grating. Right? It's exactly the same. And so if you tested this would actually be a way, if you knew the wavelength of your X-rays, you could then calculate the size of the atoms. Or if you knew the size of your atoms, you could calculate the wavelength of the X-rays, assuming that they are just electromagnetic waves. And so you performed that experiment, and it was able to verify both of these guesses were probably true, that atoms were around that size, and that they were arranged in this lattice structure, and that X-rays had to be electromagnetic waves. But the important bit, right, it's exactly the same mathematics, right? Exactly the same mathematics, the same way that visible light, diffraction, and diffraction grating is what happens for X-rays going through a crystal lattice. Notice that the reason that it's a little bit different, right, X-rays are much smaller wavelength, and the atoms are much smaller spacings between sort of your slits, right? The visible light, we had, say, 600 nanometer wavelength light and something like 0.1, well, about 10 to the negative 6th meters or so slit sizes, right? Remember that from the experiment we did. And so this sort of scales down the same way, right? The atom size is about the same size, about 10 times bigger than the wavelength. This is why visible light won't diffract in an atom. It's too big of a wavelength. So this picture is probably the most important thing, right? This is kind of what you're looking at, right? If you have a crystal of certain structure and X-rays are shined in on it, right? There is a spacing d between each atom. That's like your slit spacing, right? This is the slit spacing. And so if we take that, we basically can just use the same wave interference equation we've used in the past to then calculate, or relate rather, the wavelength and the slit spacing, or the atomic spacing. So a simplified view of that would be this, right? Actually, I'm going to go to the next one. That's a bit better detail, right? This is sort of a side view. And if you shine X-rays in from some source over here, then they're going to come in, right? You don't have a point source. You have like a ray source. You have multiple rays. Some of them will go between the slits, right? Some of these rays will make it between the atoms, and they'll just keep going. Some of them will hit the atoms and reflect, right? And we know the law of reflection, right? These angles are all the same. And since these rays are all parallel, every single theta is exactly the same, right? And so when they come back out on this side, whether you see a lot of bright light or no bright light is an interference condition based on the path length difference, which is calculable from the geometry, right? If I compare the two rays, right, ray 1 and ray 2, we see that the only difference in their paths is this little bit right here, right? Everything prior to that, right, everything there is the same, everything there is the same. And similar, because all the atoms are regularly spaced, this right here is 2d cosine theta, and so on. So whatever the path length difference is, right, if this is delta r, then this is 2 delta r, and so on, right? It's exactly twice as much. So if this is constructive, then this by definition must be as well, and so on. We saw that with the diffraction gradient, very similar derivation. So we can calculate then where are the bright spots based on the wavelength and the atomic spacing d, which is what we care about. Right? And this is just, again, remind you, diffraction is exactly the same. That's still a wave property. This doesn't really change that. So we can put this together. This is called Bragg diffraction specifically. The terminology isn't super important. You should notice, though, right, this right here is the path length difference, and this is the interference condition. Right? This is the geometry, and this is the wave interference. Right? Exactly the same as we saw before. But because the geometry is different, the equation itself is a little bit different. Right? This is not directly on the AP sheet. You have to be able to derive it from what you have, but you know, it's very similar. It's quickly derived from one that is there. Notice as well, you can only calculate where the bright spots are, right? Everything in between is dim. And so there are also, right, there are multiple bright spots, right? The first, second, third, and so on. So if you know sort of where bright spots are located, the angle, then you can figure out sort of the atomic spacing given the wavelength, or the wavelength given the atomic spacing, right? It's an experimental way to figure out the structure of things. So I'm going to walk briefly through this practice problem, but all it really is using that equation. Right here, right, we know the wavelength, we know where maxima are. And from this experiment, we should be able to determine sort of how the atoms are organized in the crystal, the solid. Right? That's just going to come from that Bragg equation. We know we have constructive interference, we know where the constructive interference is, and we know the wavelength of the X-rays. So this is sort of overly simplified, but notice where this comes from, right? This is really two equations. So we have 2d cosine theta is m lambda, right, which we're going to apply twice. So 2d cosine theta 1 equals m1 lambda, and 2d cosine theta 2 is m2 lambda. Now, we don't know m1 or m2, but we do know that they're related, that m1 and m2 differ by 1, right? So what's happened here with this equation is they've just divided the two equations by each other. So we have 2d cosine theta over 2d cosine theta. We'll call this theta m plus 1 and theta m. And we divide the other side, which is m plus 1 over m, lambda, and lambda. And notice that when you do that, right, the two d's cancel and the lambdas cancel, and that's where they get the equation that they have right there. Right? And so this tells us m plus 1 over m is 3/2. And so now we know that m plus 1 is 3 and m equals 2. Right? That's handy because now we can take our value of m and substitute it into the equation, which is what you do right here, and then rearrange to solve for d. Right? And notice that, right, we get a very small number. That should make sense. One of the hardest parts about these quantum physics problems is that the numbers are, inaccessibly small. 0.185 nanometers is very, very small. But when you're getting atomic level or size things, you should expect less than a nanometer. Nowhere else, though. Okay? So the next bit is, again, a bit more of historical background and context for this. This is an immensely powerful tool, immensely powerful. Not all crystals are as simple as that example, right? The description of the crystal lattice was a simple cubic. There are many, many, many ways to arrange atoms in a lattice that are not simple cubic, but if you understand the geometry, you can use this idea of diffraction and the path length difference to calculate the interference conditions for any of them. And so you can figure out where bright spots happen for any complicated solid that you want, assuming that you have a big enough sample of it and you know sort of what structure it is. Or, right, you can work the other way around. If you know the spacing but not the structure, you can use the interference condition that results to figure out what crystal structure must have sort of given rise to that bright spot. And specifically, this was used for figuring out the shape of the DNA molecule. And this picture is very famous, right? This is the original data that sort of shows the X-ray diffraction pattern for DNA. And unfortunately, I would love to describe it in more detail, but it's interpreting that is an immensely hard task. But you can see that there's repeated spots. That's sort of the repeating pattern, the helical pattern, as I recall. And so these kind of hints and glimpses at the atomic structures from interference let us learn the structure of some very complicated and important molecules. And this is still how proteins are figured out as well. Proteins are similarly complicated. And so it's a very practical tool, right? That we can't see atoms directly, but this is a way to see them indirectly. But in the end, really all you're doing is using the diffraction tools we practiced before, just with smaller wavelengths and smaller slit spacings. It doesn't really change the math.